Hello class, this week we'll be learning how to compare two groups. First we'll learn how to compare two population proportions. Next we'll learn how to compare two population means. And then we'll learn how to calculate confidence intervals for the difference between two population proportions. And then we'll learn how to calculate confidence intervals for the difference between two population means. And we'll be doing this as usual in SPSS. The data set which we'll be using is the North Carolina birth data, which we've used a few times now. You should be familiar with those variables and the data by now. And the reading for this week was chapter 10. So I'm assuming you've read that before viewing this lab. And also, I'm assuming you've reviewed the lecture slides. So it should be clear that the explanatory variable in this case is dichotomous. It's a categorical variable with two groups. Those two groups will be comparing proportions or means depending on whether the response variable or outcome is categorical or quantitative. For a categorical response variable, we'll be comparing proportions. For a quantitative response variable, we'll be comparing means. Now, the first analysis which we'll be conducting in SPSS is to compare two population proportions. Now, the outcome or response variable in this case is a dichotomous categorical variable. Now, dichotomous meaning two groups or binary, which is low birth weight. So we have two populations here, those mothers who smoked and those mothers who do not smoke. And what we would like to do is compare the proportion of low birth weight babies. And we want to know whether or not they are equal or different. And in SPSS, if you look at your variable view, you'll see low birth weight and smoke. Those are the two variables we'll be using. Now, low birth weight, the response in this case, or the outcome, or the dependent variable, is coded as 0, 1. Now, 1 indicates an infant was low birth weight, 0 indicates infant was not low birth weight. Now, this is important because that enables us to use the independent samples t-test function in SPSS. And also, we need to do that to make sure that SPSS calculates the mean or proportion correctly, because if you recall from page 274 in your text, the mean of a dichotomous variable or a categorical variable, which is categorized as 0, 1, is simply the probability of the outcome designated by 1. So in this case, the outcome designated by 1 is infant was low birth weight. So if we were to ask SPSS to calculate the mean for this value, low birth weight, if we were to ask it to calculate the mean for low birth weight infant, the mean value that it would provide would be the probability of 1, or the probability of the outcome designated by 1, which in this case is low birth weight. So this is telling us that 9% of our sample are low birth weight infants. Now we can confirm that. We can go to our analyze frequencies. We can look at the numbers for low birth weight. We can see 70 out of our 800 were low birth weight infants, which is 9%. So the probability of a low birth weight infant being 0.09 or 9%. If we had our variable coded differently, instead, for example, as 1, 2, we would SPSS would not calculate the mean correctly, or as the mean would not equal the proportion or the probability of the outcome designated by 1. So, for example, if we were to look at sex here, sex of a child, the value, if you see, is coded as male, female. So if we were to ask SPSS to calculate the mean for this variable, it would not equal the proportion designated by 1. Now I can show you that here. If I asked it to calculate the mean of the sex of the child, we see here it gives us a mean of 1.48, which actually is not the probability of the outcome designated by 1, in this case male. If we were to go to our frequencies, we can see that the probability of the outcome male is actually 0.523, or 52.3%. So you can see that that's not what SPSS gave you when you had your variable coded as 1, 2. So you need to have your variable coded as 1, 0, your outcome variable in this case. So we get the mean calculated correctly, or the proportion calculated correctly. And also that enables us to use this independent samples t-test function in SPSS. Now I don't want to go too much into the math on that, why we're able to do that, but for those who are interested, I pulled up a website via a Google search. This is a Dr. Jonda who works for, I believe, Northwestern University. I'm sure there's other Google sites or websites that have this information, but this is the first one I saw which came up, which had a pretty good description. So I'm sharing that with you if you want to pause and read here why we can use independent samples t-test to test for differences in proportions as well as in means. There's a brief description here. There's also a worked out example here on the next page, which you can pause again and go through. You can stop and read this page. Now for those who are interested, you can do that, but just know that we need to have our response variable coded as 1, 0 before we use this independent samples t-test. Now you can use Chisquare Test, which we'll learn about later on when our response variable has more than 2 categories, meaning 3 or more. We'll be learning how to use Chisquare Test. We can also use Chisquare Test when our outcome has 2 categories, which we have in this case, which we'll see on the next page. We use the SPS function for Chisquare Test. So we'll learn both cases here. The first case, we are going to use independent samples t-test, and let's take a look at our question. Are mothers who smoke during pregnancy more likely to have low birth weight infants compared to mothers who do not smoke during pregnancy? So, although I want to note one thing here, although in this question here, there is an indication of direction. So for instance, if you were to see this in the homework, you would know that it's indicating direction. It's a one-tail test. I'm going to use an example. I'm going to keep it as a two-tail test. We are simply looking to see if the proportion is different in the two groups. So we're going to use a two-tailed test. But you should be familiar with the difference between a one-tailed and a two-tailed and how it affects your null and alternative and how it affects your p-value. But for the most part, I'll be dealing with two-tailed tests. So let's learn how to do that in SPSS. First thing we'll be doing here is stating our null and alternative, and we'll be setting our significance level at 0.05. In SPSS, we're going to go to our Analyze, Compare Means, Independent Samples t-test. Our test variable, which is our response variable, or our outcome, or our dependent variable, is low birth weight infant. Now the two groups which we'll be comparing are mothers who smoked to those who did not smoke. So our variable here, smoke during pregnancy, we're going to move under grouping variable. Now we need to tell SPSS the values for our categories. So in variable view, if you go to smoke, we can see that the two values for this variable, 0 indicates a mother did not smoke, a 1 indicates a mother did smoke. So we have to tell SPSS, let's say the first group is 1, second group 0. So that corresponds to the coding we used for our variables. We're going to click continue, and in options we're going to leave it at default confidence interval 95%, click continue, and we are going to click OK. Now in this case we are looking at an output with two separate rows values. So keep in mind that the standard error when you're comparing proportions is calculated differently when you conduct a hypothesis test versus when you calculate a confidence interval. You'll see that later on in the hand calculations. The standard error when you are calculating a confidence interval will be 0.033, and the standard error when you are conducting a hypothesis test will be 0.029. So when you are getting your z-score and your p-value for your hypothesis test, you're going to look in the row labeled equal variances assumed. The z-score here 1.789 and the two-tailed p-value of 0.074. Our p-value indicates that we would fail to reject our null. It's greater than our alpha of 0.05. That says that we are saying that it's possible that the two population proportions are the same. So we can construct a confidence interval for the difference between two population proportions to see to get a precision of our estimate. As we learned last week, we want to know the actual value, which we say could possibly be 0, which is why you see here 0 is within this confidence interval. So the findings of our hypothesis test are consistent with what we obtain from the confidence interval. So the hypothesis test, we fail to reject a null, which means that we are saying that it's possible that the population proportions are the same, meaning their difference is 0. Now, when we constructed a confidence interval for the difference between the two population proportions, it contained a 0, meaning that the difference between the two, it's possible that it is 0, which is consistent with what we concluded from our hypothesis test. So don't make the mistake of getting all of your values from the same row. You need to get them from different row because the standard errors are calculated differently when you're conducting a hypothesis test versus when you're calculating a confidence interval. So those are highlighted here. Next, we'll learn how to conduct the same analysis via the chi-squared test. We'll learn much more about chi-squared later on. But to do that, we're going to go to our Analyze, Descriptives, Crosstabs. Now, it doesn't really matter which is in your row and column, but we're going to move smoke during pregnancy to our row. Typically, the explanatory variable is in the rows, and our outcome or response variable are in the columns, but it doesn't really matter. In the columns, we're going to move our low birth rate variable here, and when we click on our statistics, we're going to check chi-square, and we're going to click continue. Now, we're not going to do exact or anything like that. We're not going to choose any other cell displays or anything like that. We'll learn more about this later on. These options here when we learn about chi-square tests. But for now, we're not going to go into any of that. We'll leave it as it is. The only thing we need checked here: statistics, chi-square. That's all we would need. We can click on OK, and we're going to get an output here. And if you see in the first row here, Pearson chi-square, we have a value of 3.197 for our chi-square statistic, and our p-value of 0.074, which is the identical p-value that we got from our independent samples t-test. So the chi-square statistic, we have to take the square root of that in order to get our z-score. So just keep that in mind. When we have a chi-square distribution with degrees of freedom equal to 1, it's the square of the z distribution. So in order to get back to the z distribution, we take the square root. So we're taking the square root of 3.197 to get 1.79, which was the same test statistic we obtained in the beginning. So we conducted a hypothesis test, and we obtained a 95% confidence interval for the difference between the two population proportions. We saw that they were both consistent. The hypothesis test led us to fail to reject the null, which meant that it was possible that the difference between the two population proportions, as indicated here, was 0. They were the same. Now we wanted a precision of our estimate of the difference. Remember, the estimate of the difference is the difference between the two population means, which in this case was 0.05. One group had a proportion of 0.13, 13%, and one group had a proportion of 0.08 or 8%. So you subtract one from the other to get the mean difference, 0.05, and we want a precision of our estimate. We can create a confidence interval for the difference between the two population proportions, and we see here that 0 is contained within that confidence interval, indicating that 0 is a possible value for the population, for the difference between the two population proportions, and that's consistent with what our hypothesis has told us. Next, we'll look at the hand calculations to confirm what we obtained in SPSS.